Today we will tackle torsional loading shafts. This is the third topic under mechanics of deformable bodies, or again, in other textbooks they use strength of materials or mechanics of materials. Now, at the end of this video or at the end of this topic, these are what is expected from everyone. One, be able to calculate maximum shear stress, shear strain, and the angle of twist for solid and hollow circular shafts using the torsion formula and polar moment of inertia. Next, determine the required dimensions for a rotating shaft to safely transmit a specified power load at a given rotational speed without exceeding the material's allowable shear stress. Now, as we dive deep into the second learning outcome, this learning outcome is quite the same as the ones we did when we do design consideration for our topics 1 and 2, analysis of stress and analysis of strain. So basically, this is what is expected from you at the end of this subject, mechanics of materials, that at the end of the day, everyone is expected to know how to design, to consider the different design considerations, the consider different parameters in order for you to come up with a good design. Let's say the maximum allowable stress that a material can exhibit, if that is if that is only the maximum stress that a certain material can handle, then what dimension will you use in order for your design. So you will incorporate factor of safety, everything. So this is what is really expected from everyone. Next, resolve internal torques and reactions in statically indeterminate shaft systems by applying both equilibrium equations and geometric compatibility conditions. So basically the same thing with what we did in analysis of strain, statically indeterminate problems. It simply means again that the amount of unknowns exceeds the amount of not amount but rather the number of unknowns exceeds the number of equation that can be generated. So as we all know from our statics, we proceed with equilibrium equations, but for these kinds of problems, uh, equilibrium equations won't be enough in solving the unknowns. So this time we'll be using compatibility equation, but however, as compared to the compatibility equations used in the analysis of strain, there will be some variations in the formula, but nevertheless the procedure in solving statical indeterminate shaft systems is still analogous to the ones we did in analysis of strain. And lastly, the last learning outcome, compare and contrast the torsional response of thin wall tubes using shear flow concepts against the warping behavior and stress concentrations found in rectangular bars. Now, in most real world cases, we use tubes or circular in shapes to transmit power. So usually all the rotating parts are made up of tubes. But nevertheless, there are certain conditions, certain times, certain scenarios wherein shapes other than circular shapes, they also exhibit or they're also subjected to torsional forces. So the question there is, if those kind of shapes, uh, torque is being applied to those kind of shapes, how are we going to solve for their angle of twist, and how big is the shear stress that these kind of material will manifest given that they are not usually circular, right? Because as you all know, usually the most used material for these kind of application, for torsional application, is circular, right? So there are those kind of examples or those kind of problems that we will be tackling here in this video. Okay. Now, in many engineering applications, members are required to carry torsional loads. Yes, of course, But in this lesson, we'll consider torsion of circular shafts. But nevertheless, we'll also tackle, like I said, torsion in rectangular bars and how much is the shear stress that will manifest inside a rectangular bar if it is subjected to this certain amount of torque, and what is the possible angle of twist. Now, because a circular cross section is an efficient shape for resisting torsional loads, circular shafts are commonly used to transmit power in rotating machinery, just like what I said a while ago. But nevertheless, we'll also discuss another important application, which is torsion of thin walled tubes. And again, also rectangular bars. Now, one thing we should also remember is the new knowledge that we're going to acquire from studying torque. It's because torsion is an introduction to problems in which stress is not uniform or assumed to be uniform over the cross section of the member. Now, if you can remember the discussion we had in analysis of stress, as we all know that normal stress, is equal to the applied load normal to the cross-sectional area, right? Now, with this formula, this one, it is assumed that the stress distribution over that area is equal because the load being applied is equally distributed over that area. That is the assumption. So assumed to be uniform. However, under torsion here, if you can notice, when you say torsion, there is twisting. And if there is twisting, you can immediately assess that the type of stress that will manifest in the material is shear, right? Because there will be twisting, there will be sliding. However, for torsion, the amount of stress distribution over your cross section, let's say if this is our cross section, later we'll have illustrations, and let's say you twist it this way, so this will be the twisting force. The amount of distribution of shear stress over this length here is not equal, but rather linearly distributed. Okay, we'll discuss that later. But nevertheless, torsion is, I would just like to reiterate that the new knowledge that we'll be gaining from studying torsion is the problems that we will be encountering is this time the assumption is stress is not uniform but rather distributed over the length that it is being applied. Okay, now the how are we going to solve for torsion? Now, derivation of the equations used in the analysis of both torsion and bending follows these steps. Now, of course, uh, the next slide will focus on how the formula is being derived. But nevertheless, you can always go over the slide. But I will make sure to discuss it in as detailed and much easier to understand as possible, because nevertheless what is quite important is how are we going to use the formula and what are the value variables stands for within that formula, right? Yeah. Okay, so we have four steps. One, make simplifying assumptions about the deformation based on experimental evidence. Now, later on, especially in torsion and rectangular bars, the values that we will be using in order to solve for the shear stress and the angle of twist is highly experimental in nature because there will be constants used, just like 9.81, all those famous constants. So it is quite very experimental in nature, right? But you don't have to memorize all those numbers later on. Next, determine the strains that are geometrically compatible with the assumed deformations. So just like what I said when during our analysis of strain that the most critical part in solving problems, statically determined problems under strain, is especially also in thermal stress, is trying to understand what is the possible elongation of the material when subjected to one, temperature increase or temperature decrease, and two, the what is the possible elongation if there is a certain applied load, right? So that is the most critical part. Also here in torsion, still those kind of analysis still applies. Then two, use Hooke's law to express the equations of compatibility in terms of stresses, because although we will be encountering different geometrical compatibility equations as compared to strain, but nevertheless, one thing that we really want to solve in these kinds of problem is the shear stresses, right? Because yeah, shear stress or stresses in general will really manifest if there is an applied load, right? There is force involved, forces involved over a certain area, right? So that is what we are really aiming for. And then lastly, derive the equations of equilibrium. These equations provide the relationships between the stresses and the applied loads, right? Because again, stress will manifest if there is an applied load, and vice versa is also true. If there is an applied load, then there is stress, right? Yeah. Okay, so basically, for the following slides, basically it shares here that if let's say for this example, this part here is fixedly rigid, therefore the blue portion here is fixedly attached to the rigid portion. Now, if this is fixedly attached and at the free end, which is here, free end, if we are to apply a twisting force, right? A torque, a twisting force, our material will rotate. Okay? Rotate following the applied direction of your twisting force. Now, if you can notice here, it moved this a certain distance. Wait, okay? Okay. Based on these observations, we can make the following assumptions. Circular cross sections remain plane and it do not warp, sorry, and perpendicular to the axis of the shaft. Now, take note that in reality, if you twist a certain material, tendency is it's either it shortens or it elongates. Especially rubber, if you try to twist that, you try to twist your arm, tendency is it kind of shortens or it kind of elongates, depending on how you twist that material. But nevertheless, the thing is, if we really have to consider the shortening of the material or the warping of the material when we apply that twisting force, it will be very difficult to really quantify. That is why, in order to derive the equations of of torque, we really have to consider some assumptions. And one of that assumption is given that the material, once your twisting force is applied, we assume that it will not warp, which is in reality again is not real. It's ideal that for a material to not do not warp if a certain if twisting force is applied. Right? Again, that is just an assumption. So again, we assume that the circular cross section of any material be also same goes applies for torsional forces, torsion in thin wall tubes, and also torsion in rectangular bars. We assume that those materials will not warp. Okay, for the sake of discussion. Next, cross sections do not deform. There is no strain in the plane of the cross section. Again, when we talk about strain here, we always associate that with shortening or lengthening. Okay, so again, there is no strain. That is the assumption. And the distances between cross sections do not change. Like what I said, in reality, usually, if you really have to twist it so hard, just imagine if you are washing your clothes and you wring it. In layman's terms, lubag. Your material really shortens, right? It warps. But because still that is twisting force, right? When you wring your clothes to let out the water, tendency is it warps, really. But for the sake of our discussion here, and for the sake of the derivation of the or formulas that we'll be using, we will assume that one, it will not warp, two, there will be no strain, and three, the differences between cross sections do not change. Okay? This is for the sake of derivation of the formulas. The deformation that results from the above assumptions is relatively simple. Each cross-section rotates as a rigid entity about about the axis of the shaft. Although this conclusion is based on observed deformation of a cylindrical shaft carrying a constant internal torque, we assume that the result remains valid even if the diameter of the shaft or the internal torque varies along the length of the shaft. Because if you can notice, if at the end here is fixed, if the material is fixedly attached, the angle of twist varies with length, right? It varies with length. Okay, so I guess this next step in deriving our formulas, this was taught already in your integral calculus, I believe, wherein you take a small strip and then you assess how that small strip behaves. You when you do area integration of areas, the volumes, right? So yeah, but nevertheless, we'll just go over this, and I'll just be focusing on the formulas that it will the formulas that we can derive from these discussions. Now, uh, since there will be twisting, there will be sliding. Like I said, there will be shear strain. And if there is shear strain, there is the relationship between shear strain and shear stress, just like the relationship between normal strain and normal stress is given by Hooke's law. For normal strain and normal stress, that's stress is equal to your modulus of elasticity times your strain. For our shear strain and shear stress, it is given by this formula. Shear stress is equal to G, which is our modulus of rigidity, is equal times the shear strain. And then here it is. Please, uh, I would like you guys to focus on this portion here. Now, if you can notice, the twisting force is applied this way, right? Twisting, uh, clockwise. Now, if you can notice, the distribution of shear stress varies linearly. At the middle part, there is no shear stress. But as you go towards the end of the surface of your uh, material, shear stress increases. Okay, now please take note also, especially to those who are yet to enroll in fluid mechanics, this analysis is also true, especially under viscosity and especially also under uh, velocity distribution over a certain column of fluid. Okay, so this analysis is the same, right? At the surface, wherein force, the twisting force is being applied, maximum shear stress manifests there. And as you go inside, as you go deeper towards the center of the earth, no joke, towards the center of your material, shear stress decreases linearly. Okay? So that is what at the introduction part wherein torsion is the introduction to problems wherein shear stress is not uniform or stress is not uniform. Okay? Nevertheless, we will be doing this derivation. You can just go over this. And ultimately, we will have this equation. Angle of twist, this one here, this is the torque twist relationship. Angle of twist is equal to TL over GJ, although in some textbooks they use angle of twist is equal to TL over JG because it is much easier to remember now when you start with J with a small the softer pronunciation than the hard pronunciation rather than we use with the strong pronunciation first G and then J. So it's better to say JG rather than GJ. Anyway, but nevertheless they're just variables that are there to represent something, and since we put the two variables side by side so they are in multiplication with each other, then you can interchange them. So TL over JG or TL over GJ. And of course, if still when we analyze the for the equilibrium equation, still we have to assume which is positive, which is negative. And if we do that, will follow what we call the right hand rule. I believe everyone encountered the term right hand rule when you enroll in statics of rigid bodies. So if let's say if this is okay, for this example here, we focus on this part, the part wherein uh, perpendicular to the cross section. So let's say this is the cross section here, and we put our right hand rule here. If you can notice, you put it on, let's say, just since you're looking at your laptop, your tablet, or your phone. So basically, let's say that is your tube. You put your right hand on top of your laptop, your phone, and then you curl your forefingers, and then the direction of your thumb, that is, if it is moving away from the surface of your laptop, your phone, your gadget in general, that is a positive torque. Of course, if the opposite is the negative torque. Okay? So yeah, that as long as it follows the right hand rule, then that is positive. Opposite to that is negative. It must be that you have to be very consistent. If your analysis, you say that you start here towards there, then every time that you do the right hand rule, as long as if you try to make a cross section, if you cut a cross section, and then if you put your uh, right hand, you assess your right hand rule, you always assume as if you are putting your right hand on top of the cross section, perpendicular to the cross section. And if the torque there is, it follows the natural curl of your fingers, then that is a positive torque. Okay. What else? And it is common practice to let the units of G, like the same thing with E when we did the analysis of strain. It is common practice to let the units of G determine the units of the other terms in the equation. Now, consistent, so if G is in PSI, therefore, your torque should be in pound inch, your length is in inch, and your J, which is your polar moment of inertia, is in inches to the fourth. In SI, of course, it is in Pascal. Now, the unit of theta, which is the angle of twist in the equation, is always radians, regardless of which system of units is used in the computation. So please be very careful. Radians. In some problem, they will ask you to report or your final answer should be in degrees. So of course, you just have to recall your trigonometry in solving or converting radians to degrees. Now, in problems where it is convenient to use a sign convention for torques and angle of twist, we represent torques as vectors. Of course, couples using the right hand rule. Okay, as discussed, a torque vector is considered positive if it points away from the cross section, and negative if it points towards the cross section. The same sign convention applies to the angle of twist. Okay, now we have derived already the torque torque angle relationship. So it means that because of the applied torque, because of the applied twisting force, as your material move at a certain angle. That's what it means, torque twist relationship. And if there is twisting involved, there is also shear that manifested within the material. So if order to calculate for the the shear stress that manifested inside the material, we are given two formulas. Now, but basically, shear is equal to TR over J. T is the torque, R is the radius, and J is the polar moment of inertia, and your tau, of course, is for your shear stress. Now, why is it there are two types of formula with two variables representing the radius? Now, as mentioned a while ago, when you say maximum shear stress, it only maximum happens at the surface. So meaning in the value of your radius that you are going to use is indeed the R, the entire R. You will use in order to solve for the maximum shear stress. However, there are certain problems wherein if let's say the radius is the radius is 5 cm, what is the shear stress at 2.5 cm, right? So basically it means when you use rho, that is basically finding the shear stress at somewhere between 0 to your maximum shear stress, or from 0 radius to radius r. Okay, so basically that's what it means lang. Because Hooke's law wasn't used in the derivation of the equations above, these formulas are valid only if the shear stresses do not exceed the proportional limit of the material in shear. And furthermore, these formulas are applicable only to circular shafts, either solid or hollow. Now, please be mindful of this, that these two formulas and also the angle of twist, which is TL over JG, is only true for circular shafts, both solid and hollow shafts. Okay, these two formulas. Now, don't worry about this formula in the box. That is basically just a simplification of the TL over J, the TR over J formula. Because again, like I said, the value of your J will be given. Okay, I will just give you the value of your J. However, it is also best to memorize it. Now, usually the problems involve J's for circles, ramampod. Okay, so the value for your J for circular shafts or for circular areas, the polar moment of circular areas is pi d to the fourth over 32, or pi r to the fourth over 2. Okay, here. And of course, if it is hollow shaft, then outer radius minus inner radius, or outer diameter minus inner diameter. So this is, again, if you try to solve for this, let's try. Uh, Shear stress is equal to TR over J, right? And then the polar moment of circular area in terms of the radius is r to the fourth over 2. So we just substitute that t r over j, which is pi r to the fourth over 2. And this becomes uh, 2tr over pi r to the fourth. This cancel out. So tau is equal to 2t over pi r cubed. And the same is true also for the solid shaft, the maximum shear stress for in terms of diameter. Okay? But okay, one thing is you just have to remember that let's solve it. Let's derive 16t over pi d cubed. Okay. We know that the formula for our maximum shear stress is Tr over J, and we know Tr over R is D over 2, right? Meaning the diameter divided by 2, so this is D2J. This is TD over 2 pi d to the fourth over 32. Then we know this becomes 32 TD over 2 pi d cubed. And this 32 becomes 16 d to the fourth. D to the fourth become cancel 2. D to the fourth becomes 3. So therefore, we can now derive this. Tau is equal to 16t over pi d cubed. If you tend to forget this formula, this one here, you just have to remember this, because again, the formula in the blue box is derived from Tr over J, and J is equal to pi d to the fourth over 32 is equal to, which is also equal to pi r to the fourth over 2. Okay, you don't have to memorize this one, you just have to memorize this and this one. Okay. Next is, if there is torque, usually there is power transmission also. Now, I believe you guys encounter this in your, you are encountering this in your dynamics of rigid body. And also, a brief introduction of this when you guys did physics for engineers. But nevertheless, the formula for power is the torque, the amount of torque, multiplied by this one, right? The angular speed and the torque, right? And we know that angular speed, which is omega, is measured in radians per unit time. So, yeah. And then frequency, if the shaft is rotating with a frequency of f, usually in hertz, is equivalent to 1 hertz, is equivalent to revolution per second, right? So omega now becomes 2 pi f, wherein the 2 pi there is the conversion from revolution to radians. Because again, omega is in radians per unit time. Okay? So therefore, this gives us P power is equal to torque times 2 pi f, or 2 pi times your frequency. Now, of course, you are to rearrange it. If for a given power, how much torque is being for a given transmitted power, how much torque does it create? So we use this formula, and then SI power usually is in watts, and watt is joules per second, and joules is Newton meter, and F is in hertz, and usually hertz is 1 revolution per second. So yeah, and then sometimes also in the US customary units, there's no problem if the power is in watts, because that is in SI. I mean, watt is a derived unit from an SI unit, which is Newton meter per second. However, for US customary, we use horsepower, and the conversion there is quite uh, laborious, because there will be a lot of random numbers. But nevertheless, you were able to encounter this in your thermodynamics when we do conversion from one unit to another, from English to SI. So as we all know that 1 horsepower is 550 pound inch per second, and which is also equivalent to 396 times 10 to the power of 3 pound inch per minute, right? And you have your guys are very good with the conversion already. But basically it means that if the power is in HP, is in horsepower, in order for us to have a uh, torque in pound inch, you use this formula. But nevertheless, you don't have to memorize this formula. What you have to memorize is the 63 times 10 to the power of 3, because again that is just derived from uh, the conversion. What you need to memorize is T is equal to P over 2 pi f. Okay, for statically indeterminate problems, for circular shafts, we have a guide procedure, because again, it really helps. It really helps. One, draw the required free body diagrams and write the equations of equilibrium. Next, derive the compatibility equations from the restrictions imposed on the angle of twist, and then use the torque twist relationships to express the angles of twist in the compatibility equations in terms of the torques, and solve the equations of equilibrium and compatibility for the torques. Okay, so basically if you try to understand the procedure, the suggested procedure, it is quite similar to the ones provided, or to the proposed procedure when we do statically indeterminate problems for strain. Okay, so we will have examples, numerous examples. So the link to the examples is provided below. Next, anyway, torsion of thin-walled tubes. Now, although torsion of non-circular shafts requires advanced methods of analysis, fairly simple approximate formulas are available for thin-walled tubes. Now, will thin-walled tubes be used in real-world scenarios? Maybe, but the purpose is, what if? It is just a manifestation that what if indeed that there will be cases wherein the material being used is the thickness is so small that if you apply a large volume of, or a large number of twisting force, it immediately broke, right? So in here the analysis is, what are the design considerations that we are going to use if indeed the material has a very small thickness. Okay, so that's what happens here. Now, the level of stress, shear stress, that a thin walled tube can handle is way smaller as compared to the shear stress that a solid or a hollow shaft can handle. That is why for thin wall tubes, there is what we call a mathematical concept that is used to relate the torque and the shear stress in this material. A mathematical concept is introduced, which is what we call a shear flow. Okay, so basically it is just a new concept that that scientists and engineers use to really to aid them in the analysis of torque or torsion in thin-walled tubes. Now, the surface that lies midway between the inner and outer boundaries of the tube is called the middle surface. This one, the dotted line, yeah, that's the middle surface. If T is small compared to the overall dimensions of the cross-section, the shear stress, sorry, this should be tau, induced by the torsion can be shown to be almost constant through the wall thickness of the tube and directed tangent to the middle surface. Okay, so since basically because of the small thickness of our material, meaning that it is assumed that the entire thickness exhibits the same amount of shear stress. So if the entire area, the entire thickness exhibits the same level of stress, meaning where does that shear stress acts is at the middle. Just like what our normal stress, how we calculate our normal stress. Because under the assumption that if let's say this is our force, this is our cross-sectional area, because under the assumption that the load being applied is applied over this entire area, we can simply represent it as a single force at the middle, right? The same is true also for this assumption under thin wall tubes. Since the shear stress, because of the small thickness of our thin wall tube, it is assumed that the shear stress in that small thickness is equal. So therefore, the shear stress acts at the middle, at the median line or the middle surface of our thickness, which is just the difference divided by 2 of our outer thickness divided by the, it's like the outer diameter divided by the inner diameter. Okay? But the word thickness, outer surface or inner surface is being used because it is not always circular. Later on, we'll encounter that there are certain shapes that being used. So for these examples under thin wall tubes, there are a lot of different scenarios. There are different figures that being used to for problems under thin wall tubes. Okay? Sige. Now, therefore, shear flow is Q. The shear flow is represented by the small letter Q, is equal to tau T. If shear stress is not constant through the walls, then shear in the equation should be viewed as the average shear stress. So this should be tau. Next, again, uh, this is just showcasing that indeed the shear flow is constant throughout the tube. So therefore, at the midline, at the median line of our thickness, that is where our shear stress is being applied. Okay. Next, if we are able to correlate the shear flow and the shear stress, where does the relationship between shear flow and torque comes in? Now, to relate the shear flow to the applied torque, consider the cross-sectional area. But nevertheless, we'll just go over this. But the formula that I would like to emphasize is this one. This is the shear flow and the shear and torque. So Q is equal to T over 2 times or twice the area naught. Now, what is our area? That is the area of the cross section that is enclosed by the median line, right? Because again, the assumption is shear stress manifested at the median surface, right? At the middle surface. And the middle surface is outlined by the median line, right? Because of the median line, that is also the middle surface, right? As provided in the in this slide. Where is it? Here. That is also the middle surface. So you have the outer surface, the inner surface, and the middle surface. And the middle surface, the length of your middle surface is called the median line, and the area that is enclosed by your median line is your area naught, or area times area sub zero. Okay, so therefore we have two formulas now for our shear flow. shear flow is equal to your tau t, and shear flow is equal to T over twice area naught. So if we want to solve for the relationship between torque and your shear stress, you can simply substitute tau t is equal to T over 2 area naught. So therefore, tau is equal to T over 2 area naught times T. Right? Yeah. Okay. So that is now the relationship between shear stress and torque. Now also, since we are able now to solve for the shear stress in terms of the force that caused the material to have shear stress, which is the twisting force or the torque, next is we are ought to derive the relationship between the amount of displacement, which is the angle of twist that is caused by the twisting force or the torque, which is this one. Theta is equal to TL over 4G area naught squared multiplied by the cyclic integration ds over t. Also, you have two formulas. It can also be TLS over 4J area naught squared T. Now, take note that S here is the median line. Then T is the thickness for that certain on where that median line is. Now, why is it that there's another formula wherein ds over T, right? Take note that later on we will realize that there are certain problems we're in that for a single thin wall tube, the dimensions of the thickness is not the same. So just a disclaimer for this one. Let's do this example, right? We have two thickness, the 2 mm thickness and the 3 mm thickness, right? So thickness 1 and thickness 2. Now, for this individual thickness, they each have their own median lines. For our 3 mm, this is its median line. And then for the 2 mm thickness, this is its median line. So what happens now is for this is given, then we have to multiply it by S1 over T1 plus S2 over T2. And that is the entire ds over T. Right? So this equation, this one is only true if the tube itself has different thickness. Okay? But if the thickness is equal for the entire tube, then basically we use this one. Okay? So we'll solve this example, and the link to the example is provided in the description below. Last topic under torsion, which is torsion of rectangular bars. Now, the analysis of circular shafts was based upon the assumption that plane cross sections remain plane and undistorted. Remember the four assumptions. However, for rectangular bars, it's quite different. If the cross-section of the shaft is not circular, experiments, right? So experimental data show that the cross-section distort and do not remain plane. Therefore, the formulas for shear stress distribution and torsional rigidity derived cannot be applied to non-circular members. Right? So if you can notice, really, you cannot use TL over JG. Okay? Now, figure 3.10, this figure here shows the distortion of a rectangular bar caused by the torque T. The two significant features of the deformation are: one, the cross-sections become distorted. Really, if you twist a foam, a foam, really it will distort. The shear strain And thus, the shear stress is zero at the edges of the bar and largest at the middle side. Right? It's the opposite for your circular. So therefore, torsion of rectangular bars has its own set of formulas. Yes, you just have to go over this, but nevertheless, this is what I want you guys to remember. The formula to calculate for the maximum shear stress that manifested within a rectangular bar under torsion is tau sub max is equal to T over C sub 1 multiplied by A multiplied by square of B. And the angle of twist is TL over all over C sub 2 A B cube G. Okay, now you might be wondering what is A, what is B, and what is this C sub 1 and C sub 2. Now, of course, G is your shear modulus. Now, A and B are the dimensions of your lengths or the sides of your rectangular bar. And always, A is the longer side and B is always the shorter side. Okay? So I hope to you guys to remember this. A is always the longer side, B is always the shorter side. So therefore, in solving torsion of rectangular bars, you always have to look for the sides. And whatever side is the longest, or whatever side is the longer, that is A. Automatically, that's A. And the shorter side is B. Now, in order to solve for your C sub 1 and C sub 2, after determining which is A, which is B, to solve for C sub 1 and C sub 2, basically you just have to divide A with B. A over B. So whatever the quotient of your division A over B, you just have to refer it here. 1, 1.2, 1.5, 2, 2.5, 3, 4, 5, 10, infinity. Now, whatever the value of A, the quotient, the ratio of A to B here, if let's say the ratio of A to B or the quotient is 1, then automatically the values of your C sub 1 and C sub 2 is 0.208, 0.141. Because again, if you can notice, as provided here in the discussion, where is it? Here. Experiments show. So C sub 1 and C sub 2 are not just random numbers, but they were obtained via tedious experimentation. Therefore, in solving torsion of rectangular bars, you don't have to worry. You don't have to memorize table 3-1. In the questionnaire itself, table 3-1 will be available. Now, when will you calculate C sub 1 and C sub 2? Because again, if your quotient A over B is in this list, 1, 1.2, 1.5, 2.0, 2.5, immediately you get the corresponding values of your C sub 1 and C sub 2. So, will there be an instance wherein you have to calculate for C sub 1 and C sub 2? Yes. That is when the quotient of your A divided by B is not on this list. When, let's say, what if the calculated value is 1.02 or 1.23? So when and how are you going to solve it? Interpolation, which is, I believe you guys are quite expert already because you did most of your interpolation in your thermodynamics too. Okay, so that is the only time wherein you have to solve for your C sub 1 and C sub 2 through interpolation. Okay, and basically that ends the discussion of torsional of loading torsion torsional of loading shafts, I believe. Torsional loading shafts. Okay, so yeah, there are a number of formulas that you have to remember. Theta is equal, which is the angle of twist for circular shafts, and that is TL over JG. The shear stress for circular shafts is TR over J, and the J is your polar moment of inertia, which is uh, polar moment of inertia, which is for circular area, that's pi r to the fourth over 2 or pi d to the fourth over 32. Okay, the next, you have also another formulas that you have to remember for uh, torsion for thin wall tubes, wherein a new concept was introduced, which is shear flow. Shear flow, Q is equal to tau T, and Q is also equal to T over 2 area naught, where area naught is the cross-sectional area enclosed by the median line. And your median line is the difference between the the inner surface and the outer surface and the inner surface. So basically the middle surface. And then you have your angle of twist also for your thin wall tube, which is TLS over 4 GA naught squared T, wherein your S over T uh, can vary if you have in your tube has different thickness, and your S corresponds to that certain thickness as well. And then another is your torsion of rectangular bars, which is the calculate for the maximum shear is T over C sub 1 AB squared, and for your theta is TL over C sub 2 AB cubed G. Okay? And also one thing to remember as well, that the distribution of your shear stress is not uniform, but rather linearly distributed over the radius. The maximum shear stress for circular shafts can manifest or happen at the surface. And at the middle, there is zero shear at the very middle. Okay, so it is linearly distributed. And just like I said, I hope you guys remember this, that the shear stress distribution is also analogous to the shear stress distribution under fluid mechanics. Especially the next subject that you will be taking is fluid mechanics. So yeah, that is all about torsion. Thank you.